Ladies and gentlemen, good morning or afternoon, depending where you are. Thank you for joining us today. Welcome to the ProTreat and Sulfur Pro Knowledge Series webinars. My name is Matt Bailey from Optimized Gas Treating, and I will be moderating today's session. Today's webinar is titled Deciphering and Making Use of Your Amine Solvent Analysis. Correctly interpreting the amine solvent analysis is crucial for efficient operation. Definitions can be confusing, and results may be misinterpreted, resulting in costly loss of operating margins, damage to equipment, environmental noncompliance, and wasted energy. With so much at stake, validating the amine analysis is paramount. This webinar will provide you a practical approach to understanding your amine solvent analysis and discuss tools to validate an amine analysis. The Knowledge Series webinar is a collaboration by three organizations: 310 Initiative Technologies from India, Canstrat President in Australia and Singapore, and OGT from the United States, who developed ProTreat and Sulfur Pro simulators for gas treating and sulfur recovery. I would like to point you all to the question box. On your screen on the left toolbar you will see a question tab. Click on it and a window will show up here. Type your question in the box below and submit it by clicking on the Ask Question button. You may enter your questions at any time during the webinar. All questions will be taken up subject to time limitations. In case we run out of time, we will send a response to your question via email. Your questions are important to us. Rest assured we will provide a response in a timely manner. You can also download technical reading material related to the webinar in the Handouts section of the webinar window. You will find technical literature as well as a summary of last year's past 8 webinars. Just want you to pay attention to the recording notice. The content of the webinar is the sole property of the organizations involved in making the presentation. The presentation is for information use only. It does not provide any warranties as such. So screen recordings or recording in any format along with screenshots or photographs is prohibited. The recording of this session will be available post-editorial changes. Our speaker for today's session will be Simon Weiland. Simon joined Optimized Gas Treating as a software development engineer in May of 2014. He completed 3 internships with OGT during his undergraduate years the summers of 2011, 2012, and 2013. Following 4 years of software development experience, Simon became a technical applications engineer in 2018, in which position he is responsible for key accounts, employee and customer training, and workshops. Simon received his BS in chemical engineering with a minor in German from the University of Oklahoma and is fluent in both English and German. He is an expert in fundamental-based modeling of sulfur recovery operations and is a subject matter expert in sulfur recovery and gas treating. With that said, we will hand it over to Simon.
Thanks for the introduction. There are really 2 ways to view an amine analysis: the business perspective and the technical perspective. The technical perspective needs to have this for unit troubleshooting and optimizing, as well as ensuring the chemistry that is in place will perform as expected. Monitoring the amine concentration in solution is important to make sure that the amine strength is what it's supposed to be. This will ensure the unit is operating optimally as per the design. One of the more important parameters to keep an eye on would be solution contaminants. This can really pack your lunch if you get some amine into your hydrocarbon products. And we've shown some butane spheres over to the right, and if you contaminate those with amine, they will need to be retreated, and this can really be a drain on profits, as you've already spent the time, energy, and money on producing the product initially, and now you have to retreat, essentially spending twice as much to get the same product. While the amine may drop out in the bottom, there's still issues with H2S and CO2, and the product will not pass the copper strip test. Emulsions and foaming can hurt operation when hydrocarbons get transported through the amine system into the sulfur plant. Hydrocarbons and sulfur plants are not good, as they cause all sorts of problems with air control, excessive thermal reactor temperatures, sooting in the converter beds, and poor quality sulfur products. You may also want to know when reclaiming is needed so the solution does not become corrosive or ineffective. From the business perspective, these are environmental control units, and when they don't work, you're either making environmental waste with the amine going out where it doesn't belong, or the products you're trying to sell are acid rain producers. When these units don't work, then you have to close the hydrocarbon supply spigot to the refinery or gas plant, and that leads to lost profit and downtime. We have people with prior OPCO experience where mistakes have cost tens of millions of dollars in lost profit when your plant is down for several months because you've made a mess of the system and turned it into Swiss cheese. This is not just capital cost. You cannot process hydrocarbon when the amine plant is down. It can even be more costly if you leak acid gas into the vicinity. These events can kill people, and those sorts of mistakes can lead to lost careers. You've got court settlements, lawsuits, businesses closing, environmental disasters. Those are the sorts of things that the managers worry about at the plants. Taking care of your plant through careful amine analysis is the best way to avoid these costly mistakes. If we have to boil down the amine analysis into critical parameters, there are really 5 areas that are important. We'll not go into heavy details on all of these, but surprisingly, the item on the top of the list is sampling. We're going to talk about what you need to do to get a proper sample, otherwise you may not be measuring what you think you're measuring. Visual characteristics can be important, and we're going to talk about this in more detail using a tool that was developed called Probot. The key concentrations you're going to pay attention to will be the amine, the dissolved acid gas components, and we'll look at a forgotten component. We'll touch on the contaminants, but this is a whole other presentation in and of itself. What you get here is how they impact the other parts of the solvent analysis. We'll talk briefly about the important parameters and what to look for there. What we'd like to spend some time on are the validation techniques and the tools that are available. Sampling is really important. You've got to get a representative sample of what's in the system. A lot of operators take a bleeder valve and grab the first sample that comes out of the line. Almost always, this is a very poor sample and does not represent the system. Shown on the right is a flange with a bunch of iron sulfide in it. Can you imagine that coming in your bleeder valve that you've pulled your amine sample from? If it's on the bottom of the pipe, like most bleeder valves are, and the pipe has been in use and it's carbon steel servicing acid gas, you're going to have iron sulfides in there. We advocate using a fast loop system. In the image here, these valves are open and you have a needle valve where you're keeping sample through this fast loop and flushed. The idea there is that when you need to sample, you've got a clean spot to grab from. You need to minimize air contamination, especially with H2S. There are systems in place where you can pre-purge your container with nitrogen. If you don't have nitrogen, you'll need to slowly fill with the sample tube, starting as close to the bottom as you can to minimize free fall agitation, and filling the bottle up as close to full as you feel safe to. This will minimize the amount of air that can possibly react with the sample. The chemistry here is that H2S in solution is mostly present as bisulfide ion, and any oxygen that is present from the air and dissolves will react to form thiosulfate irreversibly. This does 2 things. It makes some of the loading disappear, so when you go and do a titration for the loading or any other test method to find out the loading, it's just not there. What you do find is thiosulfate heat-stable salt. So you think you have more heat-stable salt present when it's really just your acid gas loading that disappeared. We have a couple of examples here for purged sample systems. Both of these have a similar operation. There's a sample inlet and a nitrogen purge optional. There's a 3-way valve, and then there's a sample bottle with a septum. If you're not catching samples at pressure, you can use this type of bottle. The vendors will typically make bottles that fit with their systems. The one on the right is a Dopac system, which is now part of Crane, and we have a brief video showing the system in operation and shows how you can pre-purge the bottle. So there's a bottle coming in, you purge the bottle, fill the bottle with sample, and then remove the bottle. It's a closed system, and there are a couple of needles that pierce the septum, not too dissimilar from milking a snake. These are just two representative systems, and we are not advocating one or the other. However, if your plant is catching samples off of a 3/4 inch bleeder, there are better and safer ways to do it. Minimizing air contamination does not only apply to catching the sample, but care also needs to be taken into account when handling the sample for testing in the lab. We've shown some techniques here to do this of varying complexity. A lot of labs don't like dealing with H2S bearing samples. However, you can do these tests in a purged hood or glove box. The basic idea here is to minimize contact with air using a number of ways. You could have made every precaution out in the plant to minimize air contamination, but if that same care is not taken into account in the lab, the sample may be compromised. One lab that comes to mind is the first step in the testing procedure was to shake the bottle vigorously to ensure a homogeneous solution. Well, if there's any amount of air in the sample bottle headspace, you've now ensured that the air is homogeneously contacting the acid gas. The other part that becomes more important in rich amine samplings is flashing loss. We made some runs using the ProTreat simulator to illustrate this effect. Flashing becomes more of an issue as the rich loadings get higher and higher. As a function of the sampling temperature in 45 weight percent MDEA, the column on the right shows what the maximum acid gas loading is that the solution can hold. You can see, at low temperature, you can hold almost 0.86 mole per mole, but if your sample is collected at 150 degrees, which is probably more reasonable for a system that is highly loaded, you can only hold 0.48 moles per mole. So, what this means is that if you have, say, 0.7 moles per mole in the process flowing in your pipe, and you catch your sample at 150 degrees, you might have 0.7 in the process, but the sample will only show and you can only ever measure 0.48 moles per mole maximum. So, how do you minimize flashing losses? Sample coolers are the most common solution. This is usually a fabricated sample cooling coil in a bucket of ice. You can also catch the sample in a Welker container. The other thing you can do is add KOH or NaOH to stabilize the sample, but you will need to take into account the volume of the strong base that you're adding into the sample. What that strong base does is stabilize the acid gas into solution. You can tell a lot just from the color and clarity of an amine sample. On the right, we have some pictures that were provided by Org Chem Group, which is an amine reclaimer. These were the samples collected around the amine reclaimer's unit feed. The clean amine, the product, which is on the right, is what you want your amine to look like, clear or slightly straw colored. The residue, or the bottle in the middle, is all of that junk that was extracted from the amine. This is everything that you don't want in the system. The feed, or the bottle on the left, is what was flowing in the amine circuit. You can see on the bottom of that feed sample bottle is some darkness, and this is probably iron sulfide that settled out of solution. When you first catch the sample, it may be darker throughout. You can also do some simple shake tests for foaming, but there are also more complicated tests you can do with an air sparger and a frit. The vendors have some standardized methods that they use to say how long it takes to break foam, and sometimes you can learn from those tests just how foamy your amine sample is. The problem with these tests is once you take the sample out of the pipe, the sample cools, solids settle, and you may not have the exact conditions that you had in the process. We've seen cases where the amine sample looks good and doesn't foam in the lab, but the system outside is actually a raging foam beast. Amine strength is a term that is thrown around commonly in the industry, and it's used synonymously with concentration of amine. But it's really a proxy for amine concentration. It's usually reporting concentration in weight percent that's supposed to represent the amine that's in solution. The precise definition is moles of base reported as weight percent equivalent of amine that you think is in solution if you titrated the sample. If you use GC or IC, that's the actual total concentration that's in solution. A lot of confusion comes when you do a titration. There are two forms of the amine. There's the free amine, which is available to react with the acid gas, and there's bound amine, which cannot react. Free amine plus bound amine is total amine. Sometimes the vendors will report the free amine as RFB, or regenerable free base. This is just the amine available to react with the acid gas. If you have acid gas or heat stable salts in the amine, total amine concentration will always be more than free amine. If you're using a pH endpoint titration or a color titrating technique, the indicator may be in a gray area where you're actually not measuring free or total, but rather somewhere in between. The Industry Amine Best Practices Group, or ABPG, did some benchmarking back in 2004. One of the members of that group took a sizable sample of DEA from their plant and sent it around to 5 different labs to analyze. The on-site plant lab measured 23.5% of amine in the solution. There were a couple of corporate labs that were engaged, and there were a couple of amine suppliers that were also engaged. And as you can see, there is considerable variability in the results that came back from this round robin testing. If you look at the actual ABPG work, the variability in these measurements depended on the titration method used, the assumptions in the titration, the definition of amine strength, some sampling interferences, and the contaminants, which affect some of the fundamental assumptions. Titrations are the method most commonly used because they are cheap and cost-effective. The simplest form is the color indicator that changes at a pH or endpoint that's a proxy for when the buffering content of the amine is gone. You can also use pH endpoint, and if you use that with a pH probe in your lab, you can automate the titration, which is a more precise way of doing the test over colorimetric, where you can have a colorblind technician, which actually happens more often than you would think. Another method that the ABPG work references, which actually removes some of the interferences, is using conductivity of the solution. So, let's talk about how the amine strength is arrived at from a titration. You have a known volume of sample that has amine and acid gas in it. We generated a virtual titration curve using ProTreat, where we know precisely what was put into the sample in the simulator. We used hydrochloric acid titrant volume and tracked the pH of the solution as the titrant was added to the sample, and this is what it looked like. The pH drops slowly at first, and when the free amine is gone, the pH rapidly drops. The tangent line, shown in red, is referred to as an endpoint. From the proxy, we can say that 1 mole of acid reacts with 1 mole of base, and we can back calculate the number of moles of base in solution. You have to assume a molecular weight of the amine to get from normality or molarity back to concentration. This was a case that we made which had 0.2 moles of H2S per mole of amine. We can get the error expectations in the amine concentration by doing a total differential error analysis. In the example from the previous slide, the absolute error in the measured amine concentration is the sum of the individual measurement errors for the titrant normality, titrant volume, and amine volume. The amine may have been pipetted into a beaker. This operation has a known uncertainty depending on the size of the pipette. The error in titer normality is usually small, but related to diluting a known standard of hydrochloric acid in a measurement flask. which is of known error. The titer volume error depends upon the size of the titration burette compared to how much sample was delivered from the burette. Typically, a difference is taken of 2 readings of known uncertainty. So let's talk about acid gas loading now. Some people refer to this as amine loading, and it's really a concentration ratio measurement. What we're doing is ratioing the moles of acid gas in solution to the moles of amine in solution. But we saw with amine strength, we can have the free or the total amine. So when we talk about the acid gas loading, we need to know the basis the amine concentration was reported in. Free amine will tend to be more conservative, but total amine is more correct. And if you're going to be plugging the information into a simulator, you need to use total amine concentration. Practically speaking, the amines we deal with will be limited, but some amines are capable of holding more than 1 mole of acid gas, as they would have more than 1 amino group. Piperazine is just one example of this. Some other terminology you might encounter might be lean, semi-lean, and rich loading. Lean would refer to low amounts of acid gas. Semi-lean would be partially stripped and is typically taken as a partial draw from a midpoint in the regenerator. And rich would be loaded amine or amine containing high amounts of acid gas. So, getting further into rich amine loading and its significance, there are some fairly serious corrosion implications with acid gas in solution. The richer the solution is, the higher the generalized corrosion is. In the simplest terms, the particles you form, which are the corrosion product, plug equipment, stabilize foam, and lead to lost profits. But what we really want to avoid is the cracking and blistering. Those events are catastrophic failures of the equipment that are hard to predict and lead to big time problems. The exchanger on the left is a carbon steel tube bundle that was exposed to rich loadings over 0.5 mole per mole. The picture on the right is a blistered contactor, and here you can see the blisters that were formed. What you have are microscopic holes, cracks, or inclusions in the steel, and when acid gas corrodes steel, you make atomic hydrogen, and this atomic hydrogen can get into those holes, where it recombines to form hydrogen gas, which will build pressure and form those blisters that you see. Most refineries have safety limits in place these days. One that is fairly common is 0.45 moles of total acid gas per mole of amine. If you need to exceed that limit, you can do that, but you're going to have to metallurgy up. Unfortunately, you're going to be paying for that in the form of capital expenditures when going from carbon steel to stainless steel, which is anywhere from 4 to 5 times more than carbon steel. So it all boils down to pay me now in metallurgy or pay me later in maintenance costs and lost profits. Now that you guys have seen a little bit of a primer on solvent analysis error, what we need to understand is how these analytical errors impact your life either as a plant engineer or as an operator. As a software supplier, we wanted to put Protreat in the middle, but in reality, Protreat is just one tool. We've got the plant people who are going to need to make moves and decisions on how to operate the plant. And if you have analytical errors, you may have to be over or under conservative. Imagine you have a rich loading limit and your loadings are low by 20%. You may be exceeding your loading limit, destroying your plant, and not knowing it. If you're doing revamps, designs, or improvements, those errors may be causing you to overcompensate when you don't need to, leading to lost profit. The simulator is used by both the operators and the engineers to help make those decisions, and the simulator is only as accurate as the data you feed it. We like to say garbage in equals garbage out. We talked about most of this already, so just a brief recap of the things that can go wrong with acid gas loadings. Remember that these are additional titrated values, which can lead to more errors. We did some work in 2009 to quantify error on acid gas loading. This is a lean amine sample that was part of the second round robin testing with the ABPG. If you want an idea as to what can be the variability, again, this is the range from the 4 to 5 labs that this was sent to. The amine concentration has fairly small deviations, but when you look at the heat-stable salts, which are the acetate through thiocyanate, these are more like order of magnitude predictions. There's 50% error in the H2S loading between the high and the low spread in the amine analysis, probably due to the H2S oxidation from not taking into account air. Even the solution pH, which is a pretty important parameter for determining the base solution capacity, has a fairly big spread. Typical expected deviation for a pH probe is plus or minus maybe a tenth. We have 4/10 here. So what happened? In our error analysis, we made some virtual titrations, and we used those titration curves to extract back what the loading would be for systems that were relatively clean and for systems with heat-stable salts and sodium content that were in the round-robin testing. And this is what you get. If you don't have other ionic contaminants, you're within plus or minus 4 or 5%. The heat-stable salt-laden systems show a lot more error because of the other things that interfere with the titration curve. In order to do this error analysis work, we had to establish the actual accuracy of the virtual titrations. We have real titration curves shown by the red dots given to us by a lab refinery, with the ProTreat predictions shown as solid lines on the graph. This is a fairly old version of ProTreat that we did this work on, but the findings are still valid and the pH titration depends on the dilution that you used. Unfortunately, by the time we got access to the data, the records were not fully known as to what the dilution was, but typical ranges are anywhere between 10 to 100 times dilution. The 100 times dilution seemed to hit the curves pretty well in this case. We could probably spend the better part of an hour talking about the merits of charge balances. However, our website has a contactor issue dealing with this topic, so I'll refer you there. You can find it at www.ogtrt.com. A copy of this spreadsheet can also be downloaded for free. The charge balanced lean H2S loading for the average of the data is in very good agreement with the measurements, right in the middle of the scatter. This indicates that while there is scatter in the data, indicating poor precision, there is minimal systematic error. If even one of the measured ion compositions is significantly off, the charge balance will tell you. Also noted are the pH predictions that compare favorably with the range of measurements reported by the 4 labs. This range is the pH range of the data from the round-robin testing. The range of pH readings you may have gotten from the vendor may be at different dilutions. ProTreat produced a pre-dilution pH close to the high range, but at 10 times dilution, the pH hits the average data point spot on. One method for coming up with real-time rich loading measurements comes from a paper that Dow recently did with LyondellBasell, whereby using the volumetric flow of the gas and the amine coming in and the delta T of the gas and the amine, you can get a rich loading. This offers some potential benefits to validate your plant measurements, or if you don't have a plant measurement, to infer what that loading is. We decided to validate by testing and fitting this equation using the ProTreat simulator. In our validation, we made a simple test system treating H2S only with a simple amine, MDEA. It was not explicitly stated, but implied in the equation that the system feed gas needed to contain water and H2S concentrations that were in small proportion to the total feed gas concentrations. We used ProTreat to create a set of case studies to generate data, and these are the ranges of inputs that were used in that case study. We looked at variable feed gas flow rates, feed gas H2S content, amine flow rate, amine strength, and we wanted to target a range of rich loadings from 0.1 to 0.6 moles per mole. We were able to validate the findings that were found in the paper by Dow and Lyon-Delbezell with an average error of plus or minus 1.7% with a maximum error of 0.45%. So the equation works. In order to set this all up, we also set up an energy balance and derived the equation ourselves. And what this equation really turned out to be is a delta loading, not an actual rich loading. So you really need to know the lean loading and add that into the delta loading to get the rich loading. The components in Dow's equation represent sensible gas enthalpy change, sensible amine enthalpy change, and a latent heat term. In that latent heat term is the heat of reaction for H2S absorption, and also the change in enthalpy when water is absorbed or removed, depending on how the column operates. On the bottom of the equation, you essentially have a proxy for the amine component molar flow. So, the top of the equation is an energy balance, which, if you know roughly the heat of absorption to H2S, can be correlated back to moles per hour of H2S, and this can be divided by the moles per hour of amine if you convert some units. So really, this equation is an elegant use of chemical engineering, and compliments to Dow and Lyon-Delbezell go out here. The other part that the latent heat term shows is that if you don't have any H2S in the feed, you're still going to change enthalpy and delta T in the column, because you're still changing the water saturation of the feed gas. And so the lambda term steers the correlation to the correct limits when there is no acid gas present. In going through the derivations of the energy balance, there are going to be some limitations to this real-time acid gas loading equation. I've listed them here for your information, but will not be covered in any level of detail. Amine solutions can have all sorts of contaminants. We've mentioned some of them, but here is a more complete list. We won't go into details here, but on the last point of other chemicals coming in, there are all sorts of things that can get into the system, including oxygen scavengers, corrosion and hydrate inhibitors from upstream wells, flow improvers, you name it, we've seen it. The component we always seem to forget about is actually the most important one, and it's the component that makes the solvent work how it's supposed to. It's not commonly known as dihydrogen monoxide. It's been blamed for all sorts of problems, and yet you can drink it out of your drinking fountain. It's one of the most fundamental and important sustainers of life, and yet it can asphyxiate you as well. This component is water. The way to measure it is by Carl Fisher, and there are ways to mess up the solution so badly that you think you might have 28% amine in the solution, and if your system is so full of heat-stable salts, you may only have 10 mole% water in the solution. And unless you measure the water content, you don't know that for sure. You don't have to always measure the water content every time you do a sample. Some vendors do, but mistakes like that can really wreck your plant. Salts can start to precipitate out in your plant if it gets too concentrated. Think about salt water or a brine solution. When your solution starts precipitating salts, it's not going to work very well for its intended purpose of acid gas treating, and can have some pretty serious corrosion implications as well. Some other important physical properties. We talked about the foaming tendency and pH already, but viscosity and density can help tell you what's in solution. The simulator can be used to check the measurements in the lab, and when they are not in agreement, you may not have everything characterized in your amine analysis. Now we're going to introduce a new tool developed by OGT called Probot. This is a COM-based spreadsheet tool used to connect ProTreat or SulfurPro to real-time plant data. This tool provides visual advice on amine hygiene, simulated pH of amine streams, and also an integrated solution charge balance. This tool also gives you virtual corrosion monitoring as well as a real-time data validation through detailed column material and energy balances. You can easily compare simulations to data and identify any needs for instrument verification and produce detailed plant performance tests. And finally, there is a detailed warning system to provide high and or low safe operating limits alarms. So now we're going to show a case study looking at a TGU system debottlenecking project to highlight how this tool was used to find the problem and propose a solution. Case study 2 was generated from a recent troubleshooting effort that OGT conducted for a plant that was full on sulfur capacity. The hydraulic back pressure of the respective Klaus TGU system was being reached. The TGU regenerator steam flow rate was maxed out. The TGU system ProTreat model is shown here. The plant is a fairly typical reduction quench amine unit running MDEA. The front end uses a reducing gas generator to furnish hydrogen with supplemental hydrogen feed. The quench tower is a single pump around loop with a main and a trim cooler. We will take a look at a few of the details of the Probot model for the amine section of the TGU. Starting with the solvent analysis, we can see that this is a 35 weight percent nominal MDEA strength system with a few thousand ppm by weight heat-stable salts. The amine is not just MDEA. There is just under 2 weight percent DEA as well that showed up in the cation chromatographic analysis. It should be noted that the H2S lean loading was below the detectable limit, and the amount of H2S used in the simulation was found by charge balance, which is detailed at the bottom of the sheet. The visual characteristics of an amine sample, color, and clarity can provide some useful information about the amine system hygiene. Probot includes a virtual visual sample bottle, which can be calibrated to an actual sample or a picture of a sample. For the current sample, note that the process advisor states the hydrocarbon levels appear to be low, and there are small microscopic iron or iron sulfide particles with some chelation. If the color of the leanamine had changed from the present yellow to moderately green, this can be simulated in our virtual sample, which has a color spectrum calibration for different treating surfaces. We will not change the clarity dimension, but this can be done as well with the horizontal adjustment slider. Notice how the process advice changes and states now that the particle filtration system should be evaluated. If we scroll down further in the solvent analysis report, we can see some additional parameters that are rolled into the charge balance and the analysis. The measured sample pH is in good agreement with the simulated pH using the measured concentrations of components in the solvent that are on this sheet. We have some basic model input next that involves the lean amine solvent rate, temperature, and pressure that comes from the DCS. Just like we saw with the Klaus example, data validation is used to condition out bad input data from the virtual plant model. Also included on this sheet are some basic parameters that can be used to roll the plant's current operating cost into the Probot report. The absorber sheet shows a sketch of the system with inlet and outlet streams. A comparison of measured to simulated data is provided where available. Some useful plots to the right are included for the current operations. The comparison of actual to equilibrium H2S shows a pinch at the top of the column. This is referred to as a lean side pinch. A lean side pinch can only be relieved by reducing the lean loading of the solvent. Since we saw already that the lean loadings were quite low, this is a useful piece of information. Further out to the right, we can see what the predicted internal temperature is for the column. If your tower is fortunate enough to have internal thermocouple measurements, these can be compared versus the model to get a sense of how well the model agrees. Further down, we have a summary of how the column is performing compared to established system-specific limits. We also see a piece of advice for this plant to consider reducing circulation subject to treating specs and objectives. Notice how the column is nowhere near jet flood or downcomer flood. A little further down yet, material and energy balances around the column are reported. The agreement is within a few percent on the material balance and energy balance. The better these are in agreement, the more faith that we can place in the digital twin's results. By tracking deviations in the material balance and energy balances over time, an indication can be made on when the next performance test may need to be scheduled, or it may be time to review instrument flow calibrations. Moving on to the Regenerator tab, we have a similarly laid out sketch with data comparison. For the sake of time, we will focus on the process advisor and what it has to say about the plant. There are several areas that the advisor flagged to take a look at. First, we can see that the system exceeded its design limits and is running beyond the design reboiler steam limit. It is also noted that the reboiler duty has room for optimization and that the column may be fouled or short of design capacity. Reflex flow has also exceeded the design limit. With this collective advice in mind, we can look at evaluating moves on the unit to relieve some of these limits. The first thing that came to mind to OGT in reviewing this data was whether the unit needed to be running so much circulation. Using the ProTreat model, we can create a side case study to evaluate dropping the circulation rate while keeping the steam rate where it is in the reboiler. For the sake of time, we've already created this case study, so I'll just show it opening up now to show how it was set up. You can see that we've taken the initial flow rate of 785 GPM and reduced it to 400 GPM in a series of 6 steps. Looking at the case study results, there is a sweet spot in the H2S treating from about 464 to 600 GPM. For a good part of this range, we're below 10 parts per million by volume H2S in the treating specification. So we could say drop the circulation rate to 500 GPM and still have plenty of cushion, where we could also consider a drop in the reboiler steam flow to lower the vapor traffic in the regenerator. We can also see where if we drop the solvent circulation, the TGU recycles less acid gas and is richer in H2S, about 5% rate. Because both of these outcomes open up room in plant capacity, they were considered worthy of trying in operations. The plant dropped rates successfully to 525 GPM without having to trigger a change authorization, which was worth several hundreds of thousands of dollars in sulfur capacity benefits. We will take one final look at the Probot model output summary. As a reminder, this was for the pre-optimized operations. We can see some of the operating cost calculations, as well as the summary of the virtual corrosion coupon calculation results. By inputting the plant-specific objectives for service life, we can see how the predicted corrosion rates and service life estimates for different areas of the plants. A red flag on the hot lean amine piping exists in this plant, and expectations for 20 years of service life may be overly optimistic. With that, we hope you've been able to get a deeper understanding of amine analyses and how they can keep your plant running smoothly, as well as help troubleshoot things going wrong at the plant. A good amine analysis combined with a state-of-the-art simulation tool like ProTreat will be able to provide information necessary to find even the toughest of problems. Thank you again for attending, and we'd be happy to take any questions you might have at this time.